Alright, this is chapter 15, section 1, and this is the classification of matter. Alright, so matter, we can classify matter into several different categories. So we start by saying, okay, matter can be either a pure substance or a mixture. So we use that term substance very loosely, or very strictly is a better term in this class. Substances can only be two things. So if you say, hey, that's a substance, well, what are we talking about? We're only talking about two things. We're talking about whether it's an element, meaning it's that 100 and what are we up to? I think we're up to like 120 elements on the periodic table. Or we're talking about the combinations of elements that make up compounds. So pure substances can only be elements or compounds. And of course we'll get into these definitions more strictly and you'll understand what an element is and a compound is more later. But elements, compounds only. And then we have mixtures are the other type of matter. And mixtures are basically where you take elements, you take compounds, and you just kind of toss them together. I kind of think about it this way in a bowl, you know. You can have a dash of this and a dash of that, and, you know, there you have mixtures. And we'll talk about the definitions of these. You can have a heterogeneous mixture, or you can have a homogeneous mixture. And so this is your basic classification of matter. Okay, so next thing we have, so we're going to define, here we go with pure substances. Pure substances are a type of matter with a fixed composition, meaning that, as we said before, it can only either be an element or a compound. That's it. Those are your only two choices. You can't have anything else within this classification itself. It has an absolutely fixed composition. It's exactly this every single time. So, if we look into elements a little bit further, elements are the basic building blocks of everything. They build all substances. Oh, sorry. Forgot to hit my pen mode. They build all substances. They're substances where all atoms are alike, meaning that when you look within that element itself, every single atom is, for example, carbon. I put an example here. So the graphite in your pencil that you're using to maybe take your notes right now, every single piece of graphite is 100% carbon. It contains all carbon atoms. Then you have the copper coating on a penny. That copper within the penny that's coating that penny, every single copper atom is copper. That's the only thing that's in it. It's 100%. The numbers we're going to use in this class, just to kind of keep consistent with the books that we're using, these numbers change from year to year, of course, with new elements that are made within the labs. So this number changes, but for the most part, there are 90 that are found on Earth, and we have about 20 that are made in labs, and that's why I use the term about, because of course those numbers change, but that's what we'll, as far as 90-20, that's what we'll use. Elements that are made in labs are usually unstable and only exist for a short period of time. So, and you got to think the reason that these atoms are even made is because they take what's called particle accelerators, and they speed up the atoms and they slam them together and then they fall apart. So you're talking that, you know, they may hold together for just nanoseconds. So from there we take compounds. or we take elements and we put them together in a fixed ratio. So where we have two or more elements combined in an exact proportion, meaning that there's always the same number of that element in this particular substance every single time. I put an example of table salt here. Table salt is NaCl, and we'll talk more about salt in general later on when we talk about ionic compounds. But table salt is NaCl, which means that there's always one sodium and one chlorine always in a grain of table salt. So that is a fixed proportion every single time. If you pick up one grain, or whatever we want to call it, one atom of table salt, you always have one sodium, one chlorine. It's just like another thing that you might be used to, H2O, which of course is water. That's always two hydrogens, one oxygen for every molecule of water. Then we have mixtures. So we're going over to, so elements, compounds, and members are pure substances. Then we have the opposite side of the spectrum, which are mixtures. Mixtures are made up of substances that can be easily separated by physical means. We'll talk about that a little bit more here in a little bit. And so you have your heterogeneous and you have your homogeneous mixtures. I think a mixture is more like we just kind of toss stuff together. We don't care about the ratios. It's, it's like a compound without caring about the ratios. Compounds are always exact quantities. You care about, it's always like water is always, 2 to 1. But mixtures, we don't care about the 2 to 1 thing. It could be, 100 hydrogens to 1 oxygen this time. It could be 2 hydrogens to 1 oxygen this time. It could be, it doesn't matter about the ratios. So, what's the difference between a homogeneous and a heterogeneous? Homogeneous contains 2 or more gases, liquids, or solid substances that blend evenly throughout. Blend evenly throughout. Now, here's what I think. I think of homo means same. So, homo means same. So, same throughout. So, I think of like when you look at this mixture, you're looking at the same mixture all the way through. It looks like the exact same thing entirety. You can't pick out the different pieces. We call these things solutions. The particles never settle to the bottom of their container. Okay. So, examples that you might have. I like to use the example of Kool-Aid. So you're making some Kool-Aid. You mix the powder, you mix the liquid, you mix it together. Can you tell the difference between the Kool-Aid and the water? No. Okay, because it blends evenly throughout. It's 2 substances that mix out. And again, does it matter what ratio? Yeah, it'll taste different depending on what ratio you mix together. But does it look any different? Yeah, it might be a little lighter and a little darker. But again, can you mix? If you put tons of Kool-Aid in there, yeah, you'll be able to pick out the Kool-Aid. But for the most part, if you use a decent ratio, you can't pick out the Kool-Aid from the water. Then you've got heterogeneous mixtures, which these are, I think of hetero, meaning like different. I'm just going to write differ. Different. So this you can distinguish easily the different pieces. I think a great example of this would be like a tossed salad. Like you go to a restaurant and you order a salad and you get the salad brought out, and particularly myself, I don't like tomatoes, I don't like cucumbers. I'm one of those people that I pick all that stuff out of my salad. So you could see those pieces most of the time and just pick them out of your salad. Those are distinguished easily within your salad yourself. You may be one of those people that don't like the croutons. You pick out the croutons. Or, you don't like that weird-looking lettuce, so you pick that weird-looking lettuce out. Whatever it may be. Okay? That's a great example. Or, another example of a heterogeneous mixture might be your pizza. Okay? You go to a friend's house, you guys all order a pizza, and to compromise, maybe you're not a pepperoni person. But you go ahead and you get, a pizza with all the meats. And you like all the meats, but you just don't like pepperoni. So you get a piece of pizza and you pick off the pepperonis. You know, again, you can easily distinguish between all the different, parts. Okay, now, we do have a couple different types of mixtures that fall within heterogeneous. A type of mixture that in which the particles are larger than those of solutions but not heavy enough to settle out. So these do not settle out. Okay, they kind of sit there. You can kind of think of this as like milk or fog, where you can kind of see like the little particles. Like if you have a little beaker here, you can kind of see the little particles, but they don't ever settle out. They're just thicker. But they're not big enough to kind of pick out. You can test a colloid by passing a light through it, a beam of light. If it's a solution, meaning if it's a homogeneous mixture, the light will go right through it. If it's a colloid and you put a light through it, I'm sorry. If it's a solution, you can't see it. If it's a colloid, sorry, my brain is only half functioning and I can't read today either, so it's not working out. The solution should go right through, and the colloid should not go all the way through. Sorry. So, and this is called the Tyndall effect. You kind of think about it like on a foggy day, can you see lights when you turn your headlights on? No. It scatters the light and makes it hard to see. Okay? And you can test this fact. Okay, we have another kind called suspensions, which also fall under the heterogeneous mixtures. And this is where your visible particles do settle. So colloids have these visible particles that don't settle, but colloids have visible particles that do not settle, and suspensions have visible particles that do settle. So this would be like your muddy pond water. You go and you get a big scoop of like muddy pond water, and you like mix it up, and then eventually it does settle out. Okay. Okay, so that should be everything for chapter 15, section 1. So just make sure that you look over all that stuff, and definitely make sure that you can classify something as an element, compound, mixture, or any of those, because it's going to be helpful later on.